Hi, let us continue with our design example of the peg footing subjected to axial loops together with the moment acting in both the major and the minor axis. We have done checking the punching shear at the perimeter of 2D from the column face. Next, we will need to check for the maximum punching shear at the column perimeter. This is another mechanism that a peg footing can fail. To do this, we need to first determine the shear force. The maximum punching shear force is taken as equivalent to the axial loops, which is 1000 kN in this case. And then this shear force is to be shared by the effective shear planes surrounding the column. Therefore, we need to determine the perimeter surrounding the column, which is U0. U0 is calculated by having the width of the column 300 mm plus 150 mm times 2 sides each. You get U0 equals to 900 mm. And then you will need to take the shear load divided by the effective area. The U0 is equals to 900 and the effective depth is taken as the average effective depth of the major and the minor axis, which we have calculated previously, equals to 513 mm. Now we need to consider the influence of the moment onto the maximum punching shear. This is reflected by a factor beta. The formula of beta is given here. You need the design moment, which in this case we have moment in both axes. Each of them have 150 kN moment. You also need the VED, which in this case equals to 1000 kN. You have the U0. We calculated as 900 mm. Now you need the K and also the W1. K we have calculated previously during the calculations for the 2D perimeter distance from the column face. This is defined by the locations of the moment. The column size parallel to the moment shall be the C1, and the column side perpendicular to the moment shall be equals to C2. For moment acting in the major axis, C1 equals to 300 and C2 equals to 150. As for the moment acting in the minor axis, the C1 and C2 swap. It is because the moment directions go in the different axes. Then you get the ratio of C1 per C2. Referring to the table, this is the same table as the one that you use for the punching shear at 2D perimeter. The ratio of 2.0 give you K equals to 0.7 and 0.5 ratio give you K equals to 0.45. That give you two different K in the major and the minor axis. Having the K number obtained, we need to find the W1. You cannot use the W1 that you have calculated for 2D perimeter, as the equations for W1 is different. You need to use this equation instead of this. Substitute C1 and C2 into the equation, you get the W1. Substitute the W1 into the equations, you get your beta. Substitute beta into the equation, you get your maximum punching shear stress. And then this maximum punching shear stress will need to be checked against the maximum shear resistance. The formula for the maximum shear resistance is given here. You can't find this formula in Eurocode, but you can find this formula in Eurocode. Through derivations, you will get this formula. In this case, we will use straight this formula. If not, you can also choose to use this formula to solve the question. They will come to the same outcome. Let us use this formula. FCK is given, which is 30. Alpha CC equals to 1.0. Partial factor of safety of the concrete is equals to 1.5. Then you get your VRD max equals to 5.28. Compare with the shear stress. The shear stress is smaller than the shear resistance, and then we know that the maximum punching shear is adequate. In the case that the shear resistance is insufficient, you will need to increase the thickness of the pad footing, engaging a larger shear areas to take the shear force. You're going to make sure the punching shear pass so that the pad footing is safe. After this, we're going to check for other serviceability requirements. This part it will be similar to what we have done previously for the other load cases. Get the thickness of the pad footing, which is 575 mm. This thickness is more than 200 mm. That means you require mechanism to have crack control on the surface of the pad footing. You can provide perimeter reinforcement along the side of the pad footing and making the reinforcement at the spacing not exceeding 200 mm. This can help to control the surface crack on the pad footing. Next, you're going to control the maximum spacing. To determine the maximum bar spacing, you need to refer to table 7.3 and Eurocode 2. From the table, you need to get the steel stress and then refers to the crack width of 0.3 mm to determine the maximum bar spacing. How do you calculate the steel stress? This is by using this formula, where there is a ratio between the quasi-permanent load against the ultimate load. However, in this case, you are only given the ultimate load without knowing how much is the GK and how much is the QK. Not having the GK and the QK, we cannot get the exact ratio. Therefore, we just simply assume that the ratio between the quasi-permanent load against the ultimate load is equals to 0.6. And then multiply the ratio between FYK divided by the partial factor of safety of the steel, which is 1.15, as reflected here. These equations also take into considerations about the area provided. There is an additional ratio of AS required divided by AS provided. The AS required, you may refer to the solutions in terms of the design of the reinforcement. These are the AS required and this is the AS provided. Because of the AS required differs, that will give you different steel stress in the major and the minor axis. And then refers to the table, do some interpolations, you get the maximum bar spacing. The calculated maximum bar spacing is 250 and 208 mm. We go for a more critical solution. choosing a smaller value of the two. And make it universal. The maximum spacing for both major and the minor axis equals to 208. Next, we need to calculate the actual spacing. This is calculated by having the width of the peg footing minus 2 sides of the cover minus half of the bar size, That gives you the distance from the first bar to the last bar, center to center, divided by total number of bar minus 1. In this case, we are providing 17 units of the bar in both directions. The width of the peg footing is 2.4 meters, also in both directions. The concrete cover is calculated as 50. 17 units of reinforcement will have 16 spacing between the bars. That's why you need to divide with n-1. The calculated spacing is 143 mm, center to center. Compare this with the maximum spacing. The provided bar spacing is less than the maximum spacing. Then the maximum bar spacing passes. And we know that the provided amount of reinforcement bar, due to the bar spacing, the surface crack at the soffit of the peg footing can be controlled to the maximum crack width of 0.3 mm. You're going to make sure every single aspect of the design of the peg footing passes. Specifically, the proposed contact surface area of the peg footing needs to be large enough so that the surface soil pressure does not exceed the soil bearing capacity. Also, you need to provide sufficient amount of reinforcement bar in order to resist the ultimate moment acting on the surface of the column. Make sure your AS provided is greater than the AS required. Also check for the AS minimum and AS maximum. Make sure the peg footing is not over reinforced, and make sure you provide sufficient amount of reinforcement bar to control crack. And then you check for the shear resistance. 3 shear resistance you need to check. First is at the shear plane located at 1D from the column face. You need to check for both the major shear plane and the minor shear plane. When the peg footing provided is in the square shape, you will have to pay more attention on the minor axis, since it's going to be more critical in most of the aspects. Calculate the shear loads from this area and this area, and check against the shear resistance. The shear resistance needs to be greater than the shear load. Later, you need to check for the punching shear at 2D perimeter from the column face. Find the locations of the 2D parameters. If it is within the peg footing, you're going to check for the punching shear. Make sure your shear resistance is greater than the shear stress. And then check the maximum punching shear at the column parameter. Now it is the perimeter surrounding the column. Make sure the shear resistance is greater than the shear load. And then check for the cracking. If the thickness of the peg footing is greater than 200 mm, provide perimeter reinforcement at the distance of not more than 200 mm center to center. This is to control the surface cracking at the side of the peg footing. Also check for the maximum spacing. The bar spacing looks to be exceeding the maximum allowable spacing in order to control the surface crack at the soffit of the peg footing. Once all these are concluded, you confirm the size of the peg footing and sketch the detailings. Indicate the locations of the reinforcements. Indicate the size and the spacing. You need to be consistent with the arrangements of the reinforcement bar as indicated by the effective depth. The main reinforcement bar, it will be closer to the soffit of the peg footing. With that, this concludes the design examples of the peg footing subjected to axial load together with the moment in both axes.